Welcome back, everybody, to a new session of Physics 4480. The topic today and also tomorrow is to look at a classic in many-body physics. And this is the Hartree-Fock theory applied to the homogeneous electron gas. This is a classic because it's one of the few cases where we have analytical equations and solutions to the Hartree-Fock problem, but also for the total energy of the system, the ground state energy. This system in 3 dimensions and 2 dimensions has functioned as a benchmark for many body theories, but it's also been an excellent approximation to properties of valence electrons and conducting electrons in metals and also in semiconductors, etc., etc. So it's a model which offers a lot of benchmark possibilities of many body theories. So people who run Monte Carlo calculations, which are often seen as the kind of best possible many body method for these type of systems, they often refer to these calculations as a benchmark and use that as a comparison for many body theories like perturbation theory, Hartree-Fock theory, etc., etc. So it's a system which has been widely studied for, I'd say, more than 60 years. And it's also the results which we get from the electron gas for the correlation energy is something which is used as the first approximation for density functional theory. And this is a quantity which we are going to derive today, which is called the local density approximation to the exchange energy. So for those of you who may be familiar with density functional theory, you have probably heard of something which is called the local density approximation. And we are going to derive these equations, and we will use the electron gas as a stepping stone towards our next topic, which is density functional theory. And we will start scratching the surface of that on Friday. So if you look a little bit at the plan for this week, the plan today is simply to go through the calculations. So it's not going to be very exciting. It's actually pretty boring. But we are going to look at how we can find the Hartree-Fock solution, the analytical expressions, and also the ground state energy. For those of you who are more familiar with nuclear physics, there is a comparable system which is called infinite nuclear matter. And if you take away protons, you have something which is called infinite neutron matter, which serves as a model for the properties of the dense matter, which we expect to see in a neutron star. And it's often used as a way to derive the energy per particle for a neutron star. And if we take the derivative of this quantity as a function of density, we get the pressure. And in a neutron star, it's actually the pressure of the gas of neutrons and with a small admixture of protons, which stands against the gravitational collapse of a neutron star. So the technicalities which you will see today, they apply equally well to infinite nuclear matter and matter as we expect to have in a neutron star. So if you replace the Coulomb interaction between electrons with a strong force, you have essentially the same kind of machinery, which you need in order to find the energy of a neutron star per particle. So the type of systems which you see here, they also provide the theoretical background for the theories of quantum liquids. So if you're looking at a system like liquid helium-3, then this is also seen as an infinite system where you can use much of the same machinery as a starting point. So we are going to go through many of these details, and we're also going to look at the calculation of the ground state energy. And then at the end, we are going to start linking this with density functional theory, which is the standard mean field theory, which is used widely in material science. It's used in condensed matter physics. It's used in atomic and molecular physics. And the developers of density functional theory, Kohn and Hohenberg, they got the Nobel Prize in physics for the developments of density functional theory. Oh, wait, I think it was a Nobel Prize in chemistry. I may be mixing it up. This was back in the 90s. I think it was in 98. Then the first midterm is actually something you can download now if you want to. I put available on Friday, but I actually made it available today. And I put a deadline on the 21st of October. And we will discuss that in more detail tomorrow. So what I wanted to do now is actually to just take go quickly through the way we are going to model the electron gas. So the electron gas, as I said in the beginning, is perhaps the only realistic model of a system of man-interacting particles that allows for an analytical solution. There are some other systems. There is an interaction which is called the Calogero-Sutherland interaction, which also allows for analytical solutions. But for an infinite system, this is the benchmark system in many-body physics. And it gives actually a pretty good approximation to the properties of valence electrons and metals. So it's a system where we have made some important assumptions. So we assume that this is a system of electrons that is not influenced by external forces, except by an attraction provided by uniform background of ions. Now, in general, these electrons are actually electrons. If you're thinking of the valence electrons, these are the electrons which give rise to conductivity properties in metals. These are electrons which see a background. If you think of a metal and a given lattice structure, and in every lattice site, there is an atom. These electrons see an atom, which sets up a field. But instead of having discretized atoms, we are assuming now that these atoms or ions or whatever they give rise to a uniform background charge. And we also assume that these ions are stationary. So the system as a whole is then seen as neutral. It means that the electrons, the number of electrons, balances the number of charges which come from the ions, so that the system as a whole is neutral. This applies also to a neutron star. So if you take away protons in a neutron star, then matter is only made up of neutrons, which are neutral. But in general, a neutron star, the way we perceive it, due to the decay of neutrons into protons, that means that there will be a small fraction of protons, but that is balanced by electrons. So in general, these infinite systems are seen as neutral ones. So we assume now, and this is a basic assumption which we're going to make about the calculations which are coming now, is that we assume that we have n electrons in a cubic box. And that means that we can bring back the solution to a particle which is set up in a box. And for the non-interacting case, we know that this is given by plane waves. So when we now come to the formalities and technicalities, we are going to bring back something which you have seen probably long time ago when you perhaps took your first course in quantum physics or quantum mechanics, a particle in a box. So I'm just going to bring back those definitions, and then we're going to look at what the energies or the kinetic energy look like when we have this system in 3 dimensions. So we are then assuming that there is a uniform distribution of this positive charge which balances the electrons. So there is a distribution of charge which is now given by the density of ions multiplied with the charge. So this quantity which you see here is simply the charge density of the system, which arises from the positive charge from the ions. And then there's a similar one from the electrons, which balances that so that we have a net zero charge. So, as I said, it's not influenced by external forces, and it's simply the forces which we have is an attraction provided by these ions and the interaction between the electrons. And here we actually have benchmark calculations from what's called diffusion Monte Carlo calculations. And in 2 dimensions, there's also another paper by Seppeli, David Seppeli from Urbana-Champaign, University of Urbana-Champaign, US, who actually pioneered the diffusion Monte Carlo calculations, which are seen as the possibly best many-body calculations. You can actually prove in the limit of long simulation times that the approximation to the system should approach the exact energy. And these calculations, both in 3 and 2 dimensions, they provide a kind of benchmark for all other many-body methods. So, as I said, this electron gas is an interesting testbed for electron correlations. And the 3-dimensional electron gas is particularly important as a cornerstone of the local density approximation in density functional theory. And in the physical world, systems similar to the 3-dimensional electron gas can be found, for instance, in alkali metals and doped semiconductors. 2-dimensional electron fluids observed on metal and liquid helium surfaces, as well as metal oxide semiconductor interfaces. And there are some technicalities which we also will see lead to results which are not that compatible with what we see experimentally. And one has to deal with the long range or the infinite range of the Coulomb interaction. We are coming back to that a little bit later. So there's another very interesting thing in condensed matter physics. And the equivalent in neutron star matter is actually a potential condensation of alpha particles. But at low density, the electrons become localized, and there is a transition to something which is called a Wigner size crystallization. So that's a new phase, and that's a direct consequence of the long-range repulsive Coulomb interactions. And at higher densities, the electron gas is normally better described as what we call a quantum liquid. And then when we are running calculations with standard many-body methods, then this interaction between electrons is normally simulated by placing particles in a box. And then we would increase the size of the box, and hopefully the influence on the final result due to the way we treat the boundaries play a less and lesser role as we increase the number of particles. So most of the many-body calculations which are run, like Monte Carlo calculations or Copper cluster calculation and many-body perturbation theory, which we will encounter, Green's function theory, etc., they are performed in a finite, with a finite number of electrons, which means that we have to extrapolate towards what we call the thermodynamical limit. So the thermodynamical limit is in this specific case, because these are systems at 0 temperature, so there's no temperature here now in these calculations, but then we extrapolate the number of particles to an infinite number of particles and the volume to an infinite volume, but the ratio between volume and the number of particles stays constant, which means that we have a constant density. And we are going to look at the calculations of the energy as a function of density, which means that we will calculate the energy per particle. Because else, if we have an infinity of particles and if the energy is an additive quantity, we are going to have infinite energy. So I just wanted to give you a very, very quick introduction to the way we are going to look at this before we now just jump into the whiteboard and look at more technical details. So we are going to have a box of a volume omega or V. So I'm going to use omega and V interchangeably in the notes which are coming. And this box has a length L, so that means that the volume is equal to L cubed. And the plane wave solution, if you just think of the kinetic energy, the plane wave solution is now given by this quant function here, where we also have the spin degrees of freedom. Now, the Hamiltonian is not going to depend on spins, which means that when we look at the spin degrees of freedom, we need to pay a little bit attention when we now are calculating the Hartree-Fock contribution to the energy and also the Hartree-Fock energies themselves. We are coming back to this. But the spins, so this is actually a tensor product between the spatial part and the spin part. And the spin part is given by the standard spinors, which you should be pretty familiar with, where we have a spin up state and a spin down state. Now, the kinetic energy does not depend on spin, and the interaction between the electrons does not depend on spin. So these are the quantities which we are going to look at now. We are going to assume periodic boundary conditions, and that puts a limit on these momenta k. And we are going now to show what the kinetic energy looks like and what the potential energy looks like. So now it's time to switch over to the whiteboard and look at some technicalities of the electron gas. And after we've gone through some of these basic technicalities, we are now going to look at the calculation of the Hartree-Fock energy for the electron gas. So any questions so far? Does this sound okay? So this is the setting of the machinery which we are going to use. And as I said, it's going to be a long detour in order to get this correlation energy, which then functions as an input to density functional theory. So if there are no questions, let's just switch to the whiteboard and start looking at the technicalities. So, as I said, the topic this week is a slightly more technical one, where we now are going to derive the energy, the Hartree-Fock energy, and the ground state energy of a system of actually infinitely many electrons. But let's quickly remind ourselves of the equation which we had for the Hartree-Fock energy. So if we now take a given state P and look at the Hartree-Fock energy, this is something which we wrote out as the integral for this one-body operator of P plus, and then we had a sum over the states below the Fermi level, which we wrote like this, and then we had the Pj, and then the interaction. So this is again another integral, where we now have an anti-symmetrized matrix element. So this was the this is the equation for the Hartree-Fock energies. Now this piece here is given by kinetic energy, which we often label with a T. So I should put hats on here so we remind ourselves that these are operators. So this is kinetic energy. And it contains also a external potential, which we have left undefined here. So this is an external potential which could depend on the spatial degrees of freedom. And so we would normally call this an external confining potential. So we have been discussing potentials like the harmonic oscillator, which you could think of trapping a given particle or number of particles. And that this potential here is something which can be applied to the system. So this is an external confining potential. We just call it just an external potential. And then in this case, we have limited ourselves to just a two-body interaction. Now, if we now look at the solution of the kinetic energy, so the kinetic energy is given by minus h bar, and if we think of the spatial representation of it, it's given by the second derivative divided by 2 times the mass of the particle. So when we are evaluating these integrals, then we need actually to include this operator in the evaluation of the integrals. Now, one thing which we are not going to derive is actually the solution of Schrödinger's equation for non-interacting particles in a box. So I'm just going to take the liberty here of reminding you of the results. So for a particle in a box, and this could be a one-dimensional box or two-dimensional or three-dimensional. In our case, this is a three-dimensional one. Then we know that the momenta are limited by specific values, so they are quantized. So what we have then if we now include with periodic boundary conditions, so this goes back to one of the very first courses you had in quantum mechanics, and one of the very first examples you saw. So we have a momentum 2, which is given by 2 pi divided by the length. And then this is given by a quantum number n1 multiplied with one of the unit vectors. So this could be the unit vector in the x direction if we are using Cartesian coordinates. And then we have an E of E2 here, plus an N3 of E3 here. Then these numbers, Ni, these are the quantum numbers for this specific system. We have 3 dimensions, so that means we have 3 quantum numbers. And these numbers take the values plus minus 1, plus minus 2, etc. And there's an infinity of such energies. This means also that when we look at the solution of this system has a solution for the kinetic energy, which is given by this momentum vector or wave number, as we call it. And it depends on the spatial degrees of freedom. And it's given by 1 divided by the volume as a normalizing factor of e to the I of k times r. So as I said, I'm not going to go through the derivation of the solution of a particle in a box with particles or many particles in a box which do not interact. So this is the wave function. And we know that when I act with a kinetic energy on this function here of r, then the energy is going to be given by h squared times k squared divided by 2m multiplied by phi of k of r. So that means that the expectation value, if I now take a state P, a given state P, where I leave it unspecified, whether this is a state above the Fermi level or below, it means that this integral is simply given by, and I'm putting vectors here, this will simply be given by h squared of p squared divided by 2m. So I hope you can forgive me if I don't remind you on how you actually got these solutions. And you can actually see that this is the energy if you simply take the derivative here. So this expectation value, if you look at it, it's actually going to be given by 1 over omega. And we have a integration over the values of r. And then we have taken the operation of the operator, the second derivative. And this is going to be given by this phi of p of r. And this is the absolute value. And since these are just plane waves, this gives us something which is just given by h squared, p squared divided by 2m. Now, there's something which we should remember now is that p squared is obviously now proportional. We can use p squared or k squared. This is proportional to n1 squared plus n2 squared plus n3 squared. If you go back to the formula for the values, the discretized values, which k can take. So this discretization comes from the fact that you are doing the calculations in a box and there are boundary conditions which the system has to obey. So this gives us, when we now look at a finite number of particles, it is going to give rise to what we will call magic numbers, or number of particles which can define the Fermi level. So this gives rise.
There's a question in the chat, by the way.
Yeah, okay, let me take a look at that one. No, I can't see that question in the chat. Did somebody put a question in the chat?
Yeah, I saw it just now, but I agree I cannot see it anymore. I think
Okay,
maybe
okay.
example sent it.
Yeah, it was just someone who said that they could hear me well. Okay, so this gives rise to what we might call magic numbers. In the same way as we have for the description of the periodic system. So let's take a closer look at this. So if we now look at the energies which we can have, so the energies will be proportional to these numbers squared. And if we now make a table with N1, N2, and N3, and then we list the possible number of electrons with spin up and spin down. So every level now is occupied by one electron with either spin up or spin down. So in the first case, the ground state would be given by this energy equal to 0. So that means that we would have 0, 0, and 0. So that's one level. And in this case, I can fill in 2 electrons. So I could now, if I think of a set of such levels, I could now think of a system with 2 electrons where my Fermi level is defined by filling in these 2 lowest line levels. So if I now go to 1 here, then I have several possibilities. I have -1, 0, 0. I have +1, 0, 0. So this repeats itself, and you see quickly now that you will have 6 possibilities. So I can have 0, -1, 0, 0, 1, 0, and then 0, 0, -1, 0, 0, and 1. So these are all the cases when this sum is equal to 1. And here I can actually fill in, so I have 6 levels, and since I can have a spin up and spin down, I can fill in 12 here. That gives me a new so-called magic number, which is going to be 14, 12 plus 2. Then it's pretty easy to see what it will look like for 2. So in the case of 2, I could have -1, -1, and 0. Obviously, I cannot have 2 because then I would get 4 as energy at least. And in this specific case, we have plus 11 more combinations. So that means that in this case, with 2, I get 24 more. And that means that I can fill in up to 38 particles here. And then if you do the counting for 3, you can then fill in an additional. So for the case of 3, you will have 16 more. You're going to get 8 combinations. So you're going to get -1, -1, and -1, plus 7 more. So with 16 more particles, then we reach a new so-called magic number, which is 54. And this continues till actually we have an infinite number of particles. So when people run this type of calculations, what they normally do is actually to simply set up a number of particles in a box and then try to go as far as you can. And then you extrapolate to an infinite number of particles. Now, the advantage of the electron gas is, however, that we can actually calculate with an infinite number of particles. So all other many-body methods, like Monte Carlo methods or many-body perturbation theory, you can actually do it in many-body perturbation theory, but it's much more difficult. But most of the many-body calculations actually run with a finite number of particles, and then you extrapolate, hoping for the best. So typically here, you would have
I have a
magic
question,
numbers.
Mohammed.
Yeah, go ahead.
So you're describing these as magic numbers, but isn't this more like the degeneracy of the
Yeah,
state or something like that?
absolutely. So if you think of a system with 54 particles, that means that you would then define the Fermi level to consist of you filling up the first 54 single particle states. And then clearly you would have many more states above this, which then could function as particle states if you think in terms of a particle hole representation. Now, the reason why you call these kind of magic numbers is that when you fill in all the states here, there is only one slater determinant. And the same here, you have one slater determinant, etc., etc. So this is one of the benefits of using this kind of hierarchy, because what you can do then, if you now look at the numbers which you have, so this kind of what we normally call closed levels or closed shells. So you have an energy shell defined by 0. You have an energy shell defined by 1, 2, and 3. So if you fill up all these shells here, you get these magic numbers, as we call them, because this mimics what you have in the description of the periodic system, or if you think of nuclear physics with so-called closed shell nuclei, which we often call as magic nuclei. So that means that we would have numbers like 2, 14, 38, 54. The next one is 66, and then we have 114, etc. So the benefit of running these calculations for the electron gas is that we have a system where we can evaluate this when n goes to infinity. So let's see how we can do that. So these are the technicalities which we're going to jump into now. Now, if we go back to this Hamiltonian which we had, there was a term which we call the external potential. So in the electron gas, this external potential is going to be given by the background charge or a continuous background given by the ions or the atoms or the molecules or whatever we are thinking of as components which define the system. So we have electrons which roam around in the system, and then they see a continuous background charge. That is an important assumption and simplification which we are making. So if we now go back to the external potential, this external potential is going to describe a background charge of ions. So this U external is something which we will now define in terms of minus E, so this is charge, and then there's an integral over the volume, and these are ions which interact, and there is a constant density of these ions. So we're assuming now that this density, which we have defined before, is just given by the volume divided by, the number of particles divided by the volume. And then we have an integral over the volume, which we have. And this is now given by an R. So an electron sees these ions, which form a uniform background charge. So we have to include the Coulomb interaction, and that's where we have the minus E. And we are making the assumption that this charge density of ions is just a constant, which then has to balance the number of electrons. So that means that we have N here, and where N is the same as the number of electrons. So N is equal to NE, and this is divided by the volume multiplied with the charge. So that's what we call the charge density. So that means that this external potential is now simply given by minus the number of particles divided by this volume times E squared, and then we have an integral over the volume of D of R divided by R minus R prime. Now, this is a quantity which we are going to calculate, but first we are now going to set up the different contributions to the Hartree-Fock energy. So if we go back to the Hartree-Fock energy, you may remember that we had a Hartree-Fock potential, which we defined to be P of U of Hartree-Fock of P. And I'm skipping the vector signs on P here. And this contains now two terms where we are summing over all states up to the Fermi level. So we would have a P of J of V of P of J. minus, and then I'm splitting up this in terms of the direct term and the exchange term. So I have a P of J of V of J of P. This is normally what we would put together in terms of an anti-symmetrized matrix element. Now we have to be a little bit careful here. So in this summation, which you see here, this summation J, and also in the definition of these states here, we do have spin. And there is one of the reasons why I bring this up is that in project number 1, you need to construct the anti-symmetrized matrix element. Now, when you do that, what you will get, and this is a table in project 1, where we can take hydrogen type of wave functions and obtain analytical expressions for the integrals without the spin degrees of freedom. So what does that mean? In many textbooks, what you will see are statements like this. We omit the spin degrees of freedom because they can be trivially reinserted. But trivially reinserted, when you read statements like that, means that you have to be a little bit cautious, because it's easy to make some small errors. So let's take a look at the first term, the direct term. So I'm not putting an anti-symmetrized sign on that. So this sum over J, this is now going to be a sum over the spatial degrees of freedom plus the spin degrees of freedom. So I'm going to write a sigma J, which can now be equal to plus minus a half. And then I have a sum over these J values, which are below what I will call the Fermi level, Kf. So this is the K, this quantity Kf, which you see here now. This Kf is defined by the table which we see here. So if the upper level is given by 2, it means that there is an energy, if we go back, which is given by this K here, and the energy will be given by K squared. So I need to square this quantity here, and I want this to be equal to 2. So that would give us 2 times 2 pi divided by L squared, and I would have to insert that one into this expression here. So when I now look at this summation, that runs over these states, including the spin degrees of freedom. So let us now take a look at what this actually means for us. So it means that there's going to be a P of sigma P. There's going to be a J and a sigma J and V, and then I have a P and sigma P, and then I have a J and sigma J. Now what you notice here is that since this is independent of spin, and the spin of P is fixed, sigma P is just fixed to either plus or minus a half. So these are the spin projections. I should actually have used M sigma as a label here, but that would just give some additional clutter in my notation. But then since I'm summing over the sigma J's, you see now that I can either have, if you look at the result, which you will have here, this means that I can have 1, 0 multiplied with 1, 0, and I will have 0, 1 multiplied with 0, 1. And both of them give us 1. And that means that the direct term is going to have a factor of 2 when we sum over spins. So if we now look at the direct term, this will actually be equal to 2. And now I'm summing over the states below the Fermi level. And I'm just skipping the spin degrees of freedom. So when you now see this notation here, P, I'm now just leaving out the spin degrees of freedom. And I'm simply thinking of the quantum numbers which you get from the discretization of the problem of a particle in a box. So there is no spin degree of freedom here. So that term is a term which now something which we can evaluate. So if you look at the calculation of that specific term, this is going to be equal to, if you look more carefully at it, it's going to contain the wave function for P. So that will have a P with a given, this is a two-body integral. So we just have to keep that in mind. So this integral here, this one, is actually going to give us, and we will see that after the break, this is going to give us a term which is equal to this one, but with an opposite sign. So it means that the direct term is going to cancel the exchange, the term which comes from the external potential. So before we are going to put in some numbers, if we now look at the exchange term which we have here, this one, you see now that if this P is a spin-up state and J is a spin-down state, so let's just write it here. So suppose now that P has a spin of 1, 0, that is P, and now this corresponds to one particle and then the same particle here. But if this one is given by 0, 1, then the exchange term is going to give rise to 0. So that means that the spin of J has to be equal to the spin of P. And since P is fixed, instead of having a factor of 2, which we got from the direct term, we're just going to get a factor of 1 only. So the exchange term is now going to be equal, and after this, we are going to take a small break. This is going to be equal to minus, and then I have a sum over this J less than KF, and then I'm going to get a P, and then J, and now I'm skipping the degrees of freedom arising from spin. So this is going to be given by that. And if I now look at the integrals here, this is now going to be given when I now insert these solutions, 1 over square root of omega of e to the I, and then this is a general state, IKR. If I introduce that one, I have now to be a little bit careful because this is an integral over d of r, but there is also an integral over d of r prime. And when we do that, and one of the r's applies to one of the particles and one of the other r's to the other, then this integral is going to look like as follows. I'm going to get a minus e, and then since I have 4 single particle states, I have 1 here, 1 here, 1 here, and 1 here. I'm going to get this volume term squared. And then I have a sum, and now I'm going to, instead, I'm going to have the sum over J less than KF. And then I'm having d of r of e to the I. And then I'm going to have a momentum J. Momentum P. That's J minus P multiplied with R. And I'm going to get a new integral over d of r prime. And then I have e of I P minus J of r prime divided by the Coulomb interaction of r minus r prime. Now, this looks nasty and complicated to evaluate. And after the break, we're actually going to evaluate these integrals. So just expect a slightly boring and tedious calculation of these integrals. But the reward is that at the end, we are going to have an analytical expression for the Hartree-Fock energy. And that analytical expression is then used to calculate something which in condensed matter physics is called the band gap. And this is something you can relate directly to experiment. One can actually extract that from experiment. Okay, let's take a small break. We started a little bit later and we went a little bit over time again. So let me just pause the. So welcome back again. Now the thing which what we are going to do in this session is simply to evaluate the integral which you see here. And there are some tricks which are useful to see, because we will also use these tricks when we are going to calculate the total energy of the system. Now the task is to set up the Hartree-Fock energy. Now, one of the things which we get from the direct term, so if we look at this specific term which we evaluated before the break, this one, which gave rise to a factor of 2 here, when we now translate that one into an integral, so let's just look at that one. This is normally called a direct term, and in Hartree-Fock theory, this is often just called the Hartree term, because the Fock term comes from the antisymmetry of the trial wave function, or the ansatz for the ground state, or the ansatz for the system in terms of oscillator determinant. So in this particular case, what we end up with then is that this specific term, when we now include the summation over all the states below the Fermi level, which we label as a Kf here, this is now given by an integral over the state functions which we have. And since this is a direct term, what we will get is simply an integral over d of r prime. And then I'm going to have 2 divided by the volume. And one of the variables, d of r, one of the integrals, is simply given by the volume itself. So when I integrate the d over r over given volume, this actually, or volume v, this gives us simply the volume v. So this integral runs now over the volume. I get rid of one of these. I'm just simply inserting plane waves. It's actually easy to see that. And we get r minus r prime. Now, the summation which we are running here, since this integral here does not depend on the quantum numbers j, then what we are doing now is that this term here is simply summing up all the electrons which fill a given level j. And if you now remember that there is a spin degeneracy, which is actually this factor of 2 here, then I get all the individual electrons multiplied with 2, which then gives us the total degeneracy which we can have. So this summation here is nothing but the sum over all possible electron states. So what I get then is simply n times E squared divided by this volume. And then I have a d over r prime, and then divided by 1 over r minus r prime. And this term here is nothing but the external potential, which is due to the ions which we have. So that means that what we end up having to calculate is actually a Hartree-Fock energy of P here, Hartree-Fock, which is given now by h squared, p squared, divided by 2m, minus the exchange term which we put up here. And I'm just going to write, I'm not going to rewrite it, so this is just a minus the exchange term. And this is going to be the Hartree-Fock energy. And if you now look at the expression which we need to evaluate, we are going to spend some time on different tricks on how we can calculate this specific term here. So the exchange term is this one. And here, of just plain laziness, I just wrote it as like an exchange term here. And this is the technicality which we are going to spend some time on now. Now, what we are going to show, so let me anticipate the result which we get. So the final result, and now I'm going to make a further simplification. I'm simply going to let P be replaced by a variable K. And we are going to get the Hartree-Fock energy, H Hartree-Fock, which is given by this kinetic energy term divided by 2m minus E squared. And then I have a volume term, omega squared. No, sorry, not that. So let's just repeat the integrals which we have. So this is going to be given by a K prime. And I'm also letting J go over to a K prime. Since we are dealing with these wave numbers. So I'm going to have an integral now, which goes like d of r multiplied with e of I of k prime minus k of r. And then I have a new integral over d of r prime. And then I have e of I of k minus k prime multiplied with r prime divided by r minus r prime. Now, what we are going to get is the following expression. So we are going to have an energy which is given by h bar squared divided times k squared divided by 2m, which is the kinetic energy, minus E multiplied with the Fermi momentum. So this quantity Kf is now something which we will label as the Fermi momentum, divided by 2 pi. And it contains one term, which is a constant, plus 2, plus, and then we have a Kf squared minus K squared, divided by K times Kf. And then I have a ln of Kf plus K divided by Kf. So this is Kf minus K. And you see now that there is a potential problem here with a logarithmic divergence when we are at the Fermi level. This is something which we will ascribe to the long-range part of the Coulomb interaction. So if we add a kind of screening term to the Coulomb interaction, then that will alleviate this logarithmic divergence which you see here. This is something we will come back to a little bit later. But now let's jump into the calculation of this fascinating term which we have here. So let's just look at how we can evaluate this one. And there's some tricks here which are actually useful to have seen, because some of you may actually end up having to calculate similar expressions. So how do we actually deal with that term? Now, there is a trick which is often used in such calculations, which sometimes can make the calculations easier, and that is to introduce a convergence factor. So how do we evaluate the exchange term? So one trick is to introduce a convergence factor. And that convergence factor is actually going to be given. So we run the calculation with something which looks like this, and it has the absolute value of the distance between the two values R. And then we perform the calculation. So then we evaluate the integral. And take the limit. So sometimes this works, actually. Take limit mu goes to 0. So that's one. Then the other thing is that if we look at this summation which we have over the volume, this is something which you may have seen in a course in condensed matter physics or in statistical mechanics or quantum mechanics. So when we have this summation here, when we take the limit where the density of states K becomes denser and denser, and omega, the volume, goes to infinity, this approaches a particular expression, so which I'm just stating here, and that is going to be given by an integral over all the values of k. So if k is just one-dimensional, this is just a d of k, a one-dimensional integral. Else, like in our case, this is a three-dimensional integral. So what does that mean when we're going to evaluate this term? So let's write down the exchange term now. So now it takes an expression which runs like e squared of omega, which is the volume, of 2 pi cubed. And then I have an integral, so I'm just putting up the integrals here. And I'm going to leave out the fact that we are integrating of a specific volume. So I'm just leaving it like this, d of r prime. And then I have my r minus r prime. And then I'm getting e of minus I, so I'm simply setting in the plane waves. There's one thing which I also need to mention now, which actually is important. And in this particular case, what we end up with is now a term which then includes times an e of I of k prime, and then I have an r minus r prime. So I can bring these terms together. And then finally, I also have an integral over, or let me just wait a moment. I think I was a little bit in a rush here. So let me just rewrite what I did here. I actually was looking at my next line in my notes. So there's going to be an e to the minus I. Let me just rewrite this. We have an integral over dk. And this is an integral over dk prime. And this is now multiplied with e of I. So I'm simply reordering the plane wave solutions times r minus r prime. And this is now multiplied with e to the I, e of minus mu of r minus r prime. Now, there's one thing which I haven't mentioned yet, which is important. If you now go back to the solution of the problem with just a kinetic energy term, which means this solution which you see here. So this is a solution to Schrödinger's equation if you only have a kinetic energy and you're looking at a particle in a box. Then the energy given by these discretized values of k is simply given by this quantity here and a plane wave function, which is the one you see here. Now there's an important aspect. So this is the solution to the non-interacting problem, and it does not need to be the solution to the full Hartree-Fock problem. Like if you go back to the discussions we had last week, we would actually then change the wave function or the solution for the Hartree-Fock equations as a function of iteration by iteration. And at the end, what we have is an energy which stabilizes and a wave function which reaches the Hartree-Fock solution. Now, there's a very important aspect here. The Hamiltonian is translationally invariant. And then this is something which we are not going to show, but you can show that. The plane wave solution is also a solution to the interacting problem. So that means that the Hartree-Fock wave functions are going to be given by plane wave solutions. So this is a consequence of the fact that the interaction is translationally invariant. You can show that, but we will not do that here. We are just going to state that this is the case. And then the only thing which we need to do then is to find the updated energies. So we can use a plane wave solution as the Hartree-Fock solution for the wave function, but we need now to find the Hartree-Fock energies. That means that we need to show this equation here. So what we are going to do now is simply to calculate this term here and then go through the various steps. So let's introduce a new variable. So we have new variables. And in this case, we're going to introduce an x, which is just an r minus an r prime. And then I'm going to introduce a y, which is simply r prime. Then I can rewrite my integral. So now what I'm going to calculate is the limit with mu goes to 0. And then I have to evaluate e squared divided by the volume. And then I have a 2 pi cubed. And then I'm having the integral over d of k prime. I'm going to have an integral over dy because that replaces r prime. And then I have an integral over d of x. And this is now multiplied with e of I of k minus k, k prime minus k, multiplied with x. And this is then again multiplied with e to the minus mu. And then I have the absolute value of x divided by the absolute value of x. So this is my next integral, which I need to evaluate. Now, if we now look at the part which contains an integral over x here, let's just single that one out. So let's just take this piece here and evaluate the integral over x. So what I need to look at now is this intermediate calculation. So which means that I have a d of x of e of I of k prime minus k multiplied with x of e of minus mu of x divided by the absolute value of x. And this is something which I now can write out in spherical coordinates. So what I would get then is an integral over x squared and dx. And then I have my d omega or d theta of sine theta of d phi. And then there is no phi dependence here. This is now multiplied with e of I, and then I have my k minus k times x. So these are the absolute values, times cosine theta, and multiplied with e to the minus mu, and this is just now the absolute value, divided by x here. So let's rewrite this one. If I now introduce, so let's now just write this as x for simplicity. So this gives us now 2 pi, and then I have an integral over x squared d of x of e of minus mu of x divided by x. And then I have to evaluate the integral from, I get a factor of 2 pi because there is no phi dependence. And then I have a d theta of sine theta multiplied with e of I, and now it's the absolute value here of k prime minus k, multiplied with x times cosine theta. Now, this is an integral which we can evaluate, and you have probably seen that one before. And this integral is actually going to be equal to 4 pi divided by mu squared plus k prime minus k squared. Now, it's actually not so difficult to evaluate that integral because you have probably seen how you would integrate up this quantity which you have here. That is simply an integral over d theta sine theta. You would simply replace that one with a d of gamma, and where gamma is equal to cosine. And then you integrate up that term. That gives you just a sine function, which depends on x and the absolute value of the difference between two momenta. And then when you have that term, you can integrate that one up again with the e to the minus mu of x term, which you have here. And you will have a term with a sine k of x. And when you integrate that one up, you get this final term here. So that means that we can now go back to the expression we started with, which is actually this term here, where we take the limit of mu goes to 0. So let's do that one. So we are now going to take the limit of mu goes to 0. And then we have an e squared divided by v of 2 pi cubed. And we have an integral which now goes up to the Fermi level because the states we are summing over or integrating over are defined by the states up to the Fermi level. So we have an integral over dk prime. And then we have an integral over d of y. And this contains now a 4 pi divided by mu squared plus the difference between k prime and k squared. Now, the last term which you have here does not depend on y. So that means that if I look at the integral over dy, that is simply something which integrates up to the volume which we have. Sorry, I should also have a volume element which I have labeled with an omega here. Now, I get a volume element which then cancels that piece, and I can take the limit with mu goes to 0. So what I get then, when I take the limit, that this is going to be equal to an e squared divided by 2 pi squared, and then I have an integral over dk prime, and this goes up to the Fermi level, up to kf here, and this is divided by k prime minus k squared. And this is something which I can open up now, and I'm plugging in the spherical coordinates. So I would have an integral over 0 up to kf, and then I have a k prime squared, a dk prime. Then, since there is no dependence on the angle phi, I get a factor of 2 pi. And then I have a d theta again of sine theta. And this is multiplied with times 1 over, and then I have a square root of k prime squared plus k squared minus 2 times k, the absolute value, k prime, times k times a cosine theta. And this quantity is obviously squared. So that means that what I get is an e squared when I plug in the constants here, I'll divide it by pi. I have an integral from 0 up to the Fermi level, and then I have a k squared, a dk, and then I have a 0 up to pi of d theta of sine theta, multiplied with 1 divided by k prime squared plus k squared. And now I'm simply replacing the absolute values with just k and k prime. So this is just 2 times k prime multiplied with cosine theta. And this is something which we can then elaborate again further on. So we get a cosine theta, it's just a plain trig, which is equal to u. And then we replace cosine theta with u in these equations. And then we are going to get an integral, which is going to look like as follows. So when I perform the calculations here, I get that this one is going to be equal to e squared divided by pi divided by k. And then I have a sum up to k, an integral up to kf of k dk. And then I have ln, and now I'm going to have a k plus k prime divided by k prime minus k. And this term here is actually squared. Now, this is again something which I now can evaluate again. And if I do that, I'm going to get the following expression. When I do all the calculations, I'm going to find that this term here is simply going to be equal to e squared divided by pi divided by k. So when I perform the final integrals, I get a kf squared minus k squared divided by 2 here, multiplied with ln, and then I have my k of f plus k divided by k of f minus k, plus a term k times kf. And if I put everything together, then I have the final expression for the Hartree-Fock energies. So the final expression for the, let's just wait a moment so you can write it down here. You will, by the way, you will find all these expressions in the lecture notes as well. So if we now collect these expressions, we are going to get an analytical result for the Hartree-Fock energy, or a state with a momentum k, or wave number k, which is given by h squared times k squared divided by 2m minus e squared, where we now collect everything, divided by pi, and then I have a term 2, and this gives a plus a kf squared minus k squared divided by k times kf, and this has an ln of k plus kf of kf minus k. And this is the analytical expression for the Hartree-Fock energy for every single particle state. Now it's useful actually to make a plot of this, because there are some things which we now can relate directly with experiment. And this is one of the strengths of the homogeneous electron gas, that these quantities which we evaluate, when we put in the right physical constants, these are expressions which we can relate directly to experiment. But let's make some intermediate rewrites of this equation here. So let's define a variable x, which we simply call for k divided by kf. So that means we have a dimensionless quantity. And I'm going to define a function which is now called f of x, which is 1/2. And you will see that I can rewrite the energies in terms of this quantity, plus 1 minus 1 over x squared, divided by 4 times x. And then I have ln of 1 plus x and 1 minus x. So if I do that, I can now rewrite my Hartree-Fock energy as follows. So my epsilon k Hartree-Fock is then something which I can rewrite as h squared of k squared divided by 2m minus 2 times e squared divided by pi multiplied by f of k divided by kf and multiplied by kf. So this is just a simple rewrite of that function. And now, why is this interesting? Now, it's interesting because I can take the ratio between the Hartree-Fock energy and the energy which I would get from just plain kinetic energy. So let us now define the non-interacting energy at the Fermi level. So that energy would just be epsilon. And we are now going to look at that energy as we're going to put a level F here. And that is simply going to be given by kinetic energy. And this is given by kf squared divided by 2m here. So what I can do now is simply to take the ratio, and I'm going to put a 0 here, not because it has 0 momentum, but simply because this is going to be the non-interacting energy at the Fermi level. So you can think of that as the 0th approach to the energy of the system. So I can now take the ratio between this Hartree-Fock energy and the energy which I have for a non-interacting system at the Fermi level. So it's just kinetic energy. And you see now quickly that if I do that, this turns into, if I divide by epsilon 0, you will see now that the only thing I get is this variable x squared here. And then when I divide it with the other terms, what I get now is the following. So I'm going to get x squared minus, and I'm going to get a 4 e squared times the mass divided by h bar squared kf times pi and f of x. Now comes a very important number, which we are going to introduce here. And this is a number which you may remember back from atomic physics. So we are going to rewrite this in terms of the Bohr radius. And the Bohr radius is a number which gives a length scale for atomic systems and also systems in condensed matter physics and molecular physics and quantum chemistry in general. So the Bohr radius is written as A0, and then it contains h squared, so just given in terms of natural constants of E squared. And if these are electrons, then the mass here is the mass of the electrons. So that sets a natural length scale for atomic systems. Now, another thing which we are going to do now is to remind ourselves of the fact that the density of electrons is given by n, the number of electrons, divided by the volume. Now, this quantity n, and this is something we will show a little bit later, but this quantity n is actually the number of states, now the density of states, or the density up to the Fermi level. And we can actually calculate that one as an integral up to kf of k squared of dk. And then we have an angle. So we would have the angle part of d theta, of sine theta, and d phi. So if you're doing this in spherical coordinates. And then I have to remember now that this comes also with a factor, which is 1 over 2 pi cubed. And when I perform the calculations here, so the k squared, when I integrate that one, that gives me 1 over 3 over k cubed. And that will give me a term which goes like the Fermi momentum cubed divided by a factor of 3. Now, when I'm doing this summation, I also need to plug in the fact that these electrons can have a spin up and spin down. So there is a degeneracy of 2. And when I calculate this integral, which you see here, this just gives me 4 pi. There is a 4 pi times 2, which gives me 8 pi divided by 2 pi cubed. So this quantity is going to be equal to kf cubed divided by 3 times pi squared. Now, this is the same as n divided by the volume which we have. And if I do that, I know also that this one is something which I can rewrite. If you're now just thinking of you plugging in the volume, and we put in the Bohr radius, and the radius of a sphere whose volume is the volume per conducting electron. So we can actually rewrite this one as a 3 divided by 4 pi times an Rs cubed. So this Rs is actually a very important quantity. This R of S here is given by the radius of a sphere whose volume is the volume per conducting electron. Or we just write this, the volume per electron. So each electron now occupies a specific volume. So that means that I can now rewrite if I take this expression here, and if I use this expression as well, I can then rewrite this Fermi momentum, Kf, in terms of constants, which are 1.92, so I'm just plugging in 3 and 4 pi, divided by Rs. And if I do that, then I can rewrite my ratio between the Hartree-Fock energy and the non-interacting Fermi energy, this quantity here, as an x squared minus, and now I can rewrite everything in terms of the volume occupied by each electron divided by a natural constant, which is the Bohr radius, which defines a natural length scale. And then there is a constant 0.663 multiplied with this function f of x. So this is one of the kind of expressions which you will see in the literature. And later we are going to run these manipulations when we are going to calculate the total energy per particle. So that means energy for the whole system divided by the number of particles. And the reason why this is interesting is that in most metals, this Rs divided by A0 takes values between 2 and 6 for most metals. So that means that we can actually now relate the Hartree-Fock energy, which we found here, to something which experimentally is called the band gap. And then we can relate actually the theoretical calculation with experiment. And one of the big success of the electron gas calculations is that this gives a pretty good first approximations to many experimental observed band gaps. So let's try to explain what this band gap is, and that's where we will stop today. So let's make a plot. And we're going to put 0 here. We are going to plot this epsilon k Hartree-Fock divided by epsilon 0. So that's the energy calculated at the Fermi level for the non-interacting case. And we are going to fix a ratio of this Rs divided by the Bohr radius, which we just put to 4. Now, if I now take the non-interacting case, and if I just put 1 here and 1 here, then we know that the non-interacting case is going to look something like this parabola here, which goes like this. So this is just the non-interacting case, epsilon 0 f. Now 1 here, so what we have on the axis here is k divided by kf. So this would be the values at the Fermi level. So there is a gap here. And this gap defines what is experimentally called the band gap. So we would say that this is the band gap for a free electron. Now, if I now plot this Hartree-Fock energy divided by the non-interacting energy, we start actually at -2 here, slightly below, -1 here. And the value which we would start at is -2.652 here. And this goes up like this, and there's a small value here. Let's just put that one, -3.26. So this will be the value at the gap here. And then this one has a slight discontinuity, and it goes up like this. This is very schematic. So what you get now, this gap which you see here, defines the band gap with the exchange term. This is the band gap with exchange. Now, what does this mean actually? So this band gap, that shows the scatter between the maximum and the minimum values in the band of the states up to the Fermi level. And this band gap is something which we can actually relate to experimental values. And what we see now is that the exchange term does actually reduce from the free electron case. We get a considerable change in the band gap from a free electron to an interacting electron. And this quantity which you see here is actually something which you can relate to experimental observations. So many experimentalists, like at the Center for Material Science, which we have, they are actually doing experiments where they try to extract informations about the band gap in metals, in semiconductors, and many, many other types of materials. So the band gap is then simply the difference which we have now between the energies. So this band gap is defined as a delta epsilon Hartree-Fock, and this is defined as the epsilon at Kf at the Fermi level, Hartree-Fock, minus epsilon K equal to 0 of Hartree-Fock. And in our case, this takes a specific value, which is 2.326. And this is a quantity which we then can relate to experimental data. And one of the biggest success of the electron gas model has actually been the fact that these quantities here are not that different from what is observed experimentally. Now, tomorrow, we are going to look at the calculation of the total energy. And even though this is a long, somewhat tedious intermezzo, the final result is one, an analytical result for the total energy, which then is often used as a starting point for benchmarking other many-body methods. But it also gives, since we are going to see tomorrow that it's only the exchange term which contributes to the total energy, like in the case of the Hartree-Fock energy, this exchange term is going to be a quantity which will depend on the density or the charge density of the system. And this is used as the first approximation to the exchange term in density functional theory. And this was a very, very important result, which was presented in the 60s when Korn and Hohenberg and Korn and Sham developed density functional theory, which is an extremely successful many-body method, widely used in atomic, in material science, in molecular physics, and in quantum chemistry. And this is a method which we will be discussing in more depth from tomorrow and on. So I'm going to stop the recording now, if that is okay with everybody.